recap. למעשה מה שאנחנו עשינו בעיקר בשיעור שעבר, אנחנו סיימנו את הנושא של פרופ, עברנו לדבר על איינשטיין. הצגנו את משפט איינשטיין. So Einstein field equation. R mu nu minus 1/2 R G mu nu is equal 8 pi G T B. And as I mentioned to you, this is the heart of general relativity. I always ask one question is what happens in Einstein's equation in 2D and 3D. So I did some homework for myself and I checked it out. Of course you can write this equation in 2D and 3D. The problem is that they will not find any solution that is not the trivial solution, namely the flat solution. And the reason is that the amount of the degrees of freedom that you have are not enough. Right? R mu nu is symmetric. You can immediately see that. So it should have only 10 degrees of freedom minus 4 for the Bianchi identity, so you end up with only 6 degrees of freedom, which is exactly the curvature in 3D. In 1D, it's even it's in 3D. In 2D, it's even worse. You only have 1 freedom. End result is you can write this equation, but the only solution you could that exists, to the best of what I read, is it's a trivial solution. So in that sense, it's not really interesting. Yes.
If you try to write the equation where you solve for R by T, R mu nu is the only, there's no R, it's just T mu nu and T. The other equation, the twin equation of that.
Not twin equation. And you can rewrite this equation and you do the right
manipulation. If you contract this with G mu nu,
yeah,
you get another equation for solving R by T and
R
T.
will be equal to T, yeah.
And there's a half there also.
Yeah.
But it's not a half, it's 1 over number of dimension minus 2. Yeah. Because at some point you do a trace of G, which is
the trace
4.
of G, yes, correct.
And in 2 dimension it's 2.
But then the G mu nu will also not give you a 4, give you a 3.
Right, exactly.
Okay.
So you have 1 over 0 in 1 dimension.
Also
in 1 plus 1.
Okay, that's 2 dimension. Okay, so
it means that you cannot calculate R mu nu from T.
That's impossible. That means that you can't do relativity in only 2 dimensions.
And so still there's the question, what happens if there's a situation which is 1 dimension in nature, like one flat mass?
Yeah, nature is 4 dimensions. I don't know what you mean by
Sorry?
Nature is 4 dimensions.
Yeah, but if you have a capacitor, we have like an infinite.
I know, but there's a fundamental difference between electricity or things that you're familiar with from condensed matter physics, where you can do like a 2-dimensional condensed matter physics and relativity. And again, the fundamental difference would boil back to the equivalence principle. It would boil back to Otto-Bosch's experiment, which means that you do not have anything that gravity always pulls, it doesn't push it.
Yeah, that's one difference, but
that's a key difference.
No,
it's a major difference. It's not unless somebody discovers, anti-gravity, something that repels back. Don't happen. That's as far as I can, as my knowledge goes. Okay. As I said, what we're going to do from here on is to discuss solutions to this equation. Okay, that's what we're going to do from here until the end of the semester. What do we mean by solutions, right? The typical problem is we know what is the distribution of matter in the somewhere in space. It can be empty. It can be 0 here, right? And we want to know what is the curvature of the space, right? So even in vacuum, right? right? The Einstein equation is r mu nu is equal to 0. Even that is extremely difficult to solve.
Why is that r mu nu is equal to 0? R mu nu means what happened?
No. Just r mu nu equal to 0 is enough. Think of that for a second.
Oh, if you take the trace of this equation.
No, it's in vacuum, right? It's Einstein's equation in vacuum.
Why, the question is why you just ignore the second term?
Don't ignore it. If I put here a 0, this will automatically be a 0. Okay? I just said this is a 0.
Okay.
Even in that most simple case,
The right hand side is 0.
if this is 0, then this will be a 0 as well.
Okay, because trace.
Just think of it for a second. Even this very simple equation, the most simple equation that you can think of, you still get very difficult. It's very difficult. So fortunately, we do have some other people solve it for us. And again, as I mentioned, okay. So first, the meaning of a solution is I'm giving you, or somebody knows what is the distribution of mass or energy in some given space, and we want to know what is the curvature of this space. Okay? Remember that the problem we had, how does the existence of mass or energy act to curve space-time? אבל זה לא כזה. נדון בזה בסוף. אפילו לא מסתכל על זה. Now I mentioned that this is extremely difficult because if I'm giving you T mu nu, right, you need to deduce somehow what is G. Then you need to calculate the first derivative of G, which is the inverse to get the affine connection, then the second derivative, then take it and contract it to get the Riemann tensor, then contract it again once, twice to get the Ricci tensor and the Ricci scalar. It's a nightmare. And it's not linear, meaning that if somebody gives you, let's say that I already know a solution or know two solutions, a linear combination of two solutions is not a solution. So we don't really know if we solve Einstein's equation. If we found all possible solutions of Einstein's equations, likely we did not. Okay. Now, another thing, which is the most beautiful story, right? So if I'm given T mu nu, right, so this is given, this is what I want to solve. If I'm given T mu nu, there's no problem for me to add here a constant, which will automatically conserve the energy. Right? What is energy conservation?
Divergence 0.
T mu nu is equal to 0, right? And d mu g mu nu is automatically 0, right? By the metric compatibility. So if I add this term, I still conserve energy. Right? There's no problem. How do we call this term? This is a cosmological constant. Why on earth would we want to add such a term? What was Einstein's motivation to introduce this term? That's a great lesson. So initially Einstein wrote this equation. This was the original equation written in 1950. And then he decided he wanted to add this term. Why? What was his motivation? Yeah.
In these days, he thought that only the Milky Way was the universe, and the universe seems like static. Right? So in a static,
Einstein believed that the universe is static. He realized this equation does not have a static solution. So he tried to enforce it to get a static solution. That's why it's a great lesson. So he added up this term. And it turns out that if you do, very fine tuning, which is something that we physicists hate, in general, right? If you do a fine tuning, then you can get a solution in a way that will give you a static universe. Okay. And then what happened? A few years later,
The universe defined. The universe.
Edwin Hubble in 1929 discovered that the universe was expanding. And that, of course, led Einstein to remove that term here, right? And that he called that the biggest mistake of his life. The fact that he was led by his belief rather than what his equation told him. Because if you would not put that, this equation would give a prediction, a testable prediction, which is the expansion of the universe. And he ignored that, and so he missed that prediction. That was, you never get the Nobel Prize for it. But the Nobel Prize was not for that. It's a very famous story. And then it was abandoned for.
The equation doesn't say that the universe is expanding.
It does say it. You don't see it. When we look for solutions, you'll see that it is expanding.
Could you contract it?
Yeah, that it's not steady. You're right. Okay. Now, so this term was abandoned for 70 years. And then what happened? No. In 1998, sorry, 37 years, 1998, two groups using data from the Hubble Space Telescope, right, many years after both Einstein and Hubble were already dead, they discovered what? The universe is not only expanding, but is accelerating. Right? Now, again, you can take this term here and move it here. So we got the minus lambda G mu nu. Right? Mathematically, it's the same. But physically, remember, this has a meaning of a geometry. This is a meaning of matter content, right? Matter or energy. So we have here an extra term with some minus sign, which means it behaves very differently than anything you're familiar with, right? Which is associated with what?
The expansion, the acceleration.
The acceleration of the universe. It's not the expansion of the universe, it's the acceleration. It's the expansion goes faster, right? It's not just that the universe is expanding, it gets faster, it accelerates. So this has a name. The name for that is it's a dark energy. Don't confuse that with dark matter. It's different things. This is called the dark energy. Now, you may be heard of. What is the theory that we use to understand matter? It's quantum mechanics, but then there is another step for that. It's called the quantum field theory, which is a merger of quantum mechanics with special relativity. Now, within the realm of quantum field theory, vacuum does have energy. Right? It's the same way as when you look at quantum mechanics, everything can be thought of as simple harmonic oscillators, and the simple harmonic oscillator in a ground state have energy. Right? It's 1/2 h bar omega is for simple harmonic oscillator in a ground state. So even if you take matter and cool it to absolute zero, it still has some energy, right? Associated with Heisenberg's uncertainty principle, essentially. Right? The same happened in vacuum. Now, I don't know, I guess you will learn quantum field theory, but I'm not sure how it's being given here exactly. According to quantum field theory, the vacuum is full of basically oscillators. Right? And the excitation is attributed to particles. Okay? So in the vacuum, for every particle there is a field, and they are in a ground state, and so there is an energy. So even vacuum has an energy, which is okay. So that in that sense, it is a prediction, right? We have an energy of the vacuum itself, right? Think of it, what it means. That's definitely counterintuitive. the more vacuum you have, the more energy you have. Okay, so as the vacuum expands, you're increasing the amount of energy that there is there, which is totally counterintuitive. You never have that in everyday life. Okay. Now, quantum field theory also tells you what should be the amount of energy that the vacuum has. And lambda U of t should be of the order of the Planck mass to the power 4. Planck mass is something like 10 to the 19 g. It's a Planck mass. So we have a prediction of the theory. We have a measured. We're seeing that from expansion of the universe from distant galaxies, distant supernovas. And there seems to be some sort of a discrepancy between the measured value and the theoretical value. Do you know what is the discrepancy?
10 to the 120.
What?
10 to the 120.
Yeah. Somebody, you did your homework, right? So lambda predicted for lambda measured is about 10 to the power of 120. Not 120, it's 10 to the power 120. So there is something really, really fundamental which nobody understands. Okay? So we know that there is there. We measure something. Very far from the theory, we know that there is something. Something does more. But nobody knows more. Cool? We still use that because that's the best description we have to explain what we see. Despite the fact that it requires fine-tuning, which is something physicists really, really don't know. Questions?
When you look at the measured lambda, it's very small.
Yeah, relative to the predicted.
Yeah.
It's actually not that small. We'll see that. If you've heard today, 70% of the energy content of the universe is the dark energy. Of course, it's increasing as the universe continues to expand, accelerate. Questions? No? Okay. So as I said, our task from here on is to solve Einstein's equation. And I already told you, in this course we'll have time to discuss two solutions, two non-solutions. One is in vacuum, which is Einstein's equation in vacuum. And the solution is called the Schwarzschild solution, the Karl-Schwarzschild. The second solution is a description of the entire universe. Now the entire universe is not empty, there are things in it. But under certain simplified assumptions, we can solve it. That's called the Robertson-Walker. And with Einstein's equation, it's called the Friedmann-Robertson-Walker. And this is the universe that we live in. This is a solution that describes the universe that we live in. This will show the expansion, Apple's law, Big Bang, cool things like that. But first thing first. So the first question is, how are we going to solve it? And again, just to ensure, solving it, I'm giving you the matter and you tell me what is that. And practically this is nearly impossible by itself. Nearly impossible, I would say, for the general case, because it's such a complicated equation. So what do we do?
The solution should be R, but you have
The solution should be G.
G.
Okay, G. If I know G, I need to know the metric. I need to know how the metric looks like. From that, I can derive everything. Once I know G, deriving of R is very simple. Just immediate. The opposite is not so simple. What do we do in physics when we have a difficult problem? What do we do here? What do we look for? Symmetries. So what we're really up to is looking for symmetries. So we go for a little bit more mass. It's not going to be a big one. Normally I spend a lecture on that, but I think because we're going slightly fast, I might spend less than a lecture. So it's called symmetries and Killing vectors. So Killing, it's not particularly deadly vectors. It's following a mathematician called Wilhelm Killing, a German mathematician that lived in the 19th century and helped us look for symmetries. As usual, the math is not particularly difficult, but the intuition is much easier. Right? We can do the physical intuition first, and then you will do the math, and then you say that what I mean is quite straightforward. So again, of course, what we want is to find a symmetry in a covariant way, meaning independent of the coordinates. Right? We look for a covariant way, which meaning coordinate independent. Symmetry of the metric. Now, first, what is a symmetry? So, a symmetry, we said that a manifold M possesses a symmetry symmetry if the geometry is invariant under a certain transformation that maps M into itself. This is called isometry. Did you encounter this before, isometry?
In other
course, in other course, not in this course. Which course? Topology. So again, the idea is very simple. Let's say I have a two sphere, right? Two sphere. I'm just looking at the surface of this. Now it's symmetric. What does it mean that it's symmetric? It means that if I'm on one point, right, and I calculate the metric, I'll get something. Now I move to another point. So I'm making a map from one point to another point. Then I calculate again the metric in another point, and I see the same thing. That means that there is symmetry in this direction, right? So if I draw that, let's say I have a ball here, right? I have a point here, and I'm mapping it to another point, and I look at G mu nu. At each point, it's the same. So if it's the same, I have a symmetry. Now, it doesn't have to be fully symmetric. For example, if my space is ellipsoid, right? It's a football surface of an American football ball, right? It's ellipsoid. Right. So here, for example, if I go from here to here, I don't see the same metric. Right? But if I go from here to here, I do see the symmetry, right? If I rotate it like that, I do see the symmetry, right? So that means that I can have isometry in a certain direction, but not necessarily in all directions. Yeah.
This symmetry property is called isometry, or this transformation is called isometry?
If I make a transformation and the metric is not changed, this is called isometry. Okay. So one simple way of knowing if I have an isometry, if I'm just looking at the metric, right, and the metric is independent on a certain coordinate, then obviously if I do a translation along this coordinate, the metric is not going to change. Right? For example, let's say that I'm looking at Minkowski's face. Right? Minus t squared plus the x squared plus the y squared plus dz squared. Yeah? Now, the metric, right, minus 1, plus 1, plus 1, plus 1, does not depend on any coordinate. Right? Yeah. So, any transformation I do would in fact be an isometry, right? So if I do a translation, x mu to x mu plus a mu, or a Lorentz transformation, right? X mu to lambda mu mu x mu, right? This would be isometries. So a generally true statement, general statement, is the following, right? If the metric G is independent on a certain coordinate, namely if d sigma G mu nu is equal to 0, I'll put a star here, just to make sure that it's a given sigma. D sigma G mu nu is equal to 0 for a fixed direction. X sigma star, then it is symmetric along the translation along X sigma star. So D sigma star G mu nu equal to 0 means that X sigma star goes to X sigma star plus A sigma star is symmetry. Yeah.
Sigma star is coordinate. Can define any point and change.
Yeah. Has to be at any point, but in a given direction.
No, but the direction can change. Like, define.
Not sure that we think.
No, it's sigma at one point to be in this direction.
No, it has to be along the same direction. That's, you'll see. Let's move on. Remember this question. You'll see that it will be accepted. Yeah.
So in flat space-time, an isometry is just either a Lorentz transformation over a translation, and there is no other isometry.
Wait, that's what we're going to derive right now. Not right now. In 20 minutes or so. We'll see. The problem is if you're seeing. Well, what I want to say here is something very simple. What I want to say is if you're looking at the metric, and you're saying that the metric is independent on a given coordinate, then you immediately know that if you make a translation along this coordinate, the metric will not change. That's all I want to say here. Now, the opposite is not true, because there can be isometries which I don't see them right away when I look at the metric. Right? For example, I'll give you an example. Right? If I see that it's not depending on the metric, right? But I know also that if I do a rotation, that's also going to be an isometry. Right? It's also not going to change anything. So I have several options to do that. Right? So that's why we need to do a more general description of symmetries. But before I want to do that, I want to point to another important point, which is that when I look at the motion of a test particle, that moves along the geodesic, if there is an isometry, then the momentum of the test particle is conserved. Right, again, let me write it down. What?
Is this like Newton's symmetry of?
It's associated, but it's not exactly. So, isometries and killing vectors.
Also talks about mad or
Sorry. Isometries and the motion of test particles. When considering a test particle that moves along a geodesic, an isometry implies that the momentum component P sigma is conserved. Conserved is a conserved quantity of motion. P sigma is a component of the momentum in the isometry. Doesn't really matter here. But okay, you're going to see that in a second. So, proof. So we start with the geodesic equation. The geodesic equation, remember that we wrote it at the second form for the geodesic equation, which was that the vector is parallel transported along a geodesic parallel to itself. Right? So we wrote it as nabla u u, which is u lambda nabla lambda u mu is equal to 0. U mu was dx mu over d tau. Right? It's a tangent vector along the path. Rather than u mu, I want to work with the form momentum. So P mu is m u mu. Then I can write that as p lambda lambda p mu is equal to 0. That's the formal momentum. Now, that goes to your question, because we have the metric compatibility, nabla lambda g mu rho equal to 0, symmetric compatibility. I can raise and lower indices as I want. Use symmetric compatibility. So we expand that. This is just p lambda d lambda p mu. Just multiplied here with the g mu and nu lower indices and use the metric compatibility. And then the minus gamma rho lambda mu p lambda p rho equal to 0. Basically, I multiply that rather than mu. I can put here a nu and multiply that by g mu. So this term here is the change of momentum along the path. This is p lambda d lambda p mu. It's just m dx lambda over d tau d lambda p mu. So you can simply write it as m d p mu over d tau. Happy? Don't look so happy. Now for the second term here, this is the first term. For that term, have gamma rho lambda mu p lambda p rho. Okay, I'm going to expand it. 1/2 g rho mu d lambda g mu plus d mu g mu lambda minus g lambda mu d lambda p rho. So I can use that.
Also the third g, so we differentiate it.
I just open up the affine connection.
Yes, the third term.
Sorry? Sorry, the new.
Yeah.
Sorry, of course. Thank you. So this is 1/2 d lambda g mu nu plus d mu g mu lambda minus d mu g lambda mu p lambda p nu. We have a symmetry between p lambda and p nu. So lambda and nu, which means that lambda and nu, lambda and nu, lambda and nu. So these two terms will cancel because I can always exchange lambda and nu. So we're left with 1/2 d mu g mu lambda. E lambda p nu. So overall, from the geodesic equation, which is this, we got m d p mu over d tau is equal to 1/2 d mu g mu lambda d lambda d mu. That's still the geodesic equation. Now, so far, I did not assume any symmetry here, really. And what do we get? Now we said that if all the metric components are independent on a single coordinate, x mu, put this x sigma, right? That means that this is 0, and that means that this is going to be conserved, which is what I promised. Right? So, if all metric coefficients are independent on the coordinate x sigma, that means that d sigma g nu equal to 0. That means that d sigma over d tau is equal to 0. As you see, as I promised you, it doesn't really matter if it's an upper index or a lower index. That is true along with geodesic, any geodesic. Again, it makes perfect sense physically when you think of it. Mathematically, it can be a little bit confusing. I don't think it's that confusing if you reach this point with this part of the course. But, you know, again, think of a plane that moves, no friction, no nothing, in a constant velocity. Right? Then the component of the velocity are conserved. Nothing changes. Astronaut, right? Don't think of a planet, maybe wrong. Think of the International Space Station. The International Space Station is flying above the Earth. Right? It's constant velocity. So none of the momentum component changes. If it was to fly on a metric which is ellipsoidal, then only the components that log the geodesic for which the metric does not change would be conserved. Yeah.
In this case, we took the geodesic equation without considering external forces, external acceleration.
It's a of a geodesic, right? There are no external forces, it just moves in. It's a generalization of a straight line. Right? We didn't put external forces. Yeah. Okay. Which immediately means that finding isometries are particularly useful when we study motion of test particles. And again, think of it in terms of an astrophysicist that look at what happens in the vicinity of a black hole. Right? We are seeing motion of gas, plasma, photons from nearby black holes. Questions, guys? This is symmetric. But this is symmetric with lambda in it. So if it's symmetric, we can exchange them. But that's what it means. Yeah. Perfect. Any further questions about that? Okay, so now I want to get the general description of the symmetries, and so that's the Killing vectors. I'm going to derive an equation which is called Killing equation. that will tell me when I have symmetry, the metric, in a coordinate independent way. I'm going to make use of what we just derived here. I'm going to erase that in a second. Is it okay? Yeah. Now let's talk about thinning vectors. It's called the general description of symmetry. So again, it's not enough to look at the metric and say that, okay, this metric is independent on a certain coordinate, so we can identify that there is a symmetry in this direction. It's great, but that would not give us the full set of isometries a metric has. So in order to develop the full set, we need something which is more general. Right? That's the purpose. So the way to do is as following. So we have this equation, dp sigma over d tau equal to 0. That is one component of the momentum. So I want to promote that into a full covariant equation. This is conservation. This is conservation of one component of the momentum. Now let us assume that the metric is independent on a certain coordinate. Assume on x sigma star. I have to be a bit careful in the way I phrase it because it can be a bit tricky. You know, if I write them in Minkowski metric in coordinates, in Cartesian coordinates, x, y, z, and t, I immediately see that it does not depend on x, y, and z. But I can also write it in terms of r, theta, and phi to also be independent on theta and phi in r. I can do a rotation. Right? So when I say independent on a coordinate, it means any coordinate, not necessarily the one that I'm already seeing in the metric. Right?
Any coordinates or in
What?
So I need to find the coordinate which in this coordinate.
The idea is that right now I'm trying to show you a
You assume
completely.
that you have a
I
coordinate.
assume that I have such a coordinate. I want to drive an equation which will always be true, even if I don't see it right now.
It's really these coordinates, and we can generalize to every coordinate.
Yes. I assume now that there is some coordinate in which the metric g mu nu is independent on. Okay? So I'm looking at the vector. Consider the vector k, which is the derivative along this coordinate. Now every vector I have v mu, d mu. Right? So in component notations, we really have k mu, which is d sigma star mu. Mu component is just delta mu sigma star. Right? I just took this one component and promoted it into a full vector by just saying, okay, I have a delta function in this direction. Now we say that k mu generates an isometry. Did you ever learn about generators, group theory in general?
Yes.
Yes, one did.
Only the mathematicians.
What?
Only
Wait.
the mathematicians.
Only mathematicians. How many of you have never seen that? How many of you have seen that? 4 see, 3 did not see,
Only
2
the
refused to admit if they saw. Okay, then never mind. What it means that I have an infinitesimal transformation. Yeah, it doesn't really matter if you see it or not. I'm going to explain it. It means that there is an infinitesimal transformation in this direction, right? That leaves the geometry unchanged. Right? So that's in geometry. So the true meaning is that we can express an infinitesimal transformation. That leaves the geometry G mu nu invariant. Relation in the direction of k mu. So we can write down now the components of the momentum in covariant form, right? So P sigma star is the component of the momentum in one direction, but now I'm going to promote it into a full vector. So P sigma star is K mu, P mu. So K mu, P. Promote the component of the momentum into a full vector. Now we have conservation of the momentum along the path. So this is equivalent to what? Means that the directional derivative along the path is 0. Right? So conservation dp sigma star over the tau equal to 0 is equivalent that directional derivative along the geodesic vanishes, which means P mu nabla mu K nu P nu is equal to 0. That goes back to the curvature we did like last week or maybe the week before that. Look at me, strange eyes. Okay, so what we need to do now is just to expand that. So P mu, nabla mu, K nu, P nu just going to open it up. P mu, P mu, K mu, nabla mu, P mu, plus P mu, P mu, nabla mu, K mu. What is that top? What is that part here? It's on the board today. P mu, nabla mu, P nu. What is that? That is the geodesic equation, which is 0. Right? This is 0. This is the geodesic equation. So we are left with P mu, nabla mu, K nu. But P mu and P nu are symmetric in mu and nu. So we can only have the symmetric part of K nu contributing. So we can write that. So 1/2 P mu, P nu, nabla mu, K nu, plus nabla mu, K nu. Because symmetry. So now I'm basically reversing the logic and say that every vector K nu that satisfies that equal to 0 means that K mu P nu is conserved along the geodesic. Okay, see what I'm doing here? So, conclusion. Conclusion. Any vector K mu that satisfies nabla mu K nu plus nabla mu K nu, or if you want K mu mu plus K mu equal to 0, implies that K nu P nu is conserved along the geodesic namely that P mu nabla mu K nu P nu is equal to 0. And this equation has a name that is called Killing equation. Actually, vector K is Killing equation. Vector K mu is called the Killing vector. Killing vector field, being fully precise. But it's really called the Killing vector. Now that goes back to what I told you, right? If the metric is independent on some direction, some coordinate, obviously there there is a killing vector along this coordinate. But if you have a vector that satisfies Killing's equation, right, that means that even if you don't see that it is independent, the metric is independent, that means that you can always find a set of coordinates in which the metric will become independent of that coordinate associated with that Killing vector. So this is a more general statement. Now, okay, I'm going to give you an example in a second. For any 2 dimensionals and above, there are more Killing vectors than dimensions. I'm going to say that in a second. And that basically goes back to your question, right? The question that you asked. Although in any certain point in space-time you can only have maximum of n independent vectors, the Killing vectors are defined along trajectories, and so they're independent globally. Let me now in my lecture notes I put another derivative of that. I prefer not to do it because I want to go on further because we have a short semester. But you'll find in my lecture notes an alternative derivation. It's taken from a different book. This I think is more aligned with the logic that we did right now. Questions before I give you the example? So if not, I'll just give you a simple example, right? A 3D Euclidean space. Example. 3D Euclidean space. The s squared is dx. The s squared is dx squared plus the y squared plus the z squared. So the metric is independent on any of the coordinates, right? X, y, and z. So automatically we have 3 Killing vectors, which will be what? So x mu 1, 0, 0. Y mu is a 0, 1, 0. Z mu is a 0, 0. Yeah. But that's not all, right? You also have rotations, right? So you have rotation. So we can write this metric, right? It's equivalent of writing it as the s squared is equal to the r squared, right? Plus r squared d theta squared plus r squared sine squared theta d phi squared. What? Exactly. Now it is independent on phi. Does depend, all the components do depend on r and theta, but not on phi. Meaning that rotation around phi, right, is going to be another isometry. So the rotation would be, Killing vector would be r is d phi. It's a Killing vector. So if we go back to Cartesian coordinates, rotation around phi is the what? Is minus y dx plus x dy. Right? Rotation around the phi direction. So if I go back to Cartesian coordinate system, how do I write down rotation around phi? R mu would be a minus y, x, and 0. Now, of course, the selection of the z-axis was completely arbitrary. You can do the same around the x-axis or the y-axis. So I can find the two other as mu would be z0 minus x, t mu 0 minus z at 1. Yeah. And it's not too difficult, but again, it's those things that you must do with your hands. You must sit down, put your hands in the mud, and start playing. I'm pretty sure that by now I don't really need to tell you. And if you do it a little bit, you see that it's not really difficult. Just you get the basic idea. Questions before we move on? Maybe I think of giving you 2 exercises. Just that you have more time to, not more time, you force you to spend more time on practicing. What do you say? Like the idea? Yes.
If you give us enough time to film.
No, I give you enough time. Just want to make sure that you know. Because we're doing a lot of math here, which is
As much as possible.
what?
As much as possible.
Okay. Somebody complains, what's your name?
Record.
Oh, okay. Any questions? Okay. So now we're going to go to the second half of the course, and we're going to introduce solution. We're going to discuss the solution to Einstein's equation. I already said it, I'll say it again. We're going to discuss 2 solutions, really. That's what we have time to discuss in this course. There are a few others. Some are more interesting than others. But for that, you either have to ask for an advanced course in astrophysics or decide you want to come and work be an astrophysicist yourself and work on other solutions. Actually, it's not just astrophysicists. Some particle physicists do it as well, but mainly with string theories. I'm no expert. So, Schwarzschild. Great name. Schwarzschild solution and black holes. What we're looking now for is solution to Einstein's equation in vacuum. Einstein's equation in vacuum. R mu nu is equal to 0. Do not get confused when we say vacuum. Right? An astronaut that is orbiting Earth is in vacuum. No, T mu nu is 0. Well, it is. T mu nu is equal to 0. That means that R mu nu is equal to 0. An astronaut orbiting Earth is in vacuum. It's subject to the gravitational field of the Earth. Okay. Now, one solution you know is Minkowski space trivial solution. Schwarzschild solution is the second most important solution, maybe the most important solution. We're going to see it will give rise to the phenomenon of black holes. We will have time to discuss black holes. You will understand what are black holes, not by what you heard from science fiction or popular science, but we'll do it properly. But there is time for that. Now you may know the story. Karl Schwarzschild was a German. Einstein wrote down his famous equation in 1915. Schwarzschild found the solution in 1916, so not too long after, just a few months after writing this equation, there was a solution. It was quite unfortunate. As you know, this was World War I. At the time, he was a soldier, fought against the Russians, got wounded, something that today would have saved him, but at that time could not be saved, and after a few months he died. So I didn't live long to see the fame of his solution. Again, as I mentioned already, since Einstein's equation is not linear, the hard part is to find a solution. Once we have a solution, we can plug it into Einstein's equation and see that whether it solves it or not. Getting one is the difficult part. Schwarzschild find one for us. There is a theorem which is known as Birchhoff's theorem. That states that the solution is unique spherically symmetric. Schwarzschild solution is a unique spherically symmetric solution to Einstein's equation in fact. Now I'm not going to formally prove it for you because it's a bit mathematical, but I am actually going to give you nearly the full proof in the derivation. So you'll see 85%, but for those of you who are mathematicians, you may not catch me up. But as a physicist, the hand-waving part would make perfect sense. So that's why I'm saying I'm not giving you the full solution, but you'll get 85% of the. I'm not giving you the full proof of the theorem, but you'll get 85% of the theorem. Okay. Let's see. So I'm not sure that I want to say. Okay, so let's start by obtaining a solution. It will take a while. I don't think we'll finish it today, but we'll do some mathematical parts today. So, derivation. We want a metric which is both static and isotropic. We look for static and isotropic metric. What's isotropic?
Independent of direction.
Right, so it looks the same in all directions. If I look here and I look here, I look the same. What does it mean? What? Yeah, that it makes sense for me to look at it in spherical coordinates. Right? So I can write it down. Being isotropic, I can write it down as d omega squared is equal to d theta squared plus sine squared theta d phi. Okay, but it's a 4-dimension, right? It's a 2-dimension, so we want something which is 4-dimension. So general form in 4D. You have to add up two more coordinates, which will be t prime and r prime. At the moment, it's just names. So I have t prime, which I'm going to call it an A, and r prime, which I'm going to call it a B, for the time being. And the metric for D, the metric can be written as ds squared is. It's okay?
Is that the cosine? The r squared tau squared.
What?
In the right.
This is t.
No, not this. form of the right equation.
The omega.
The omega squared.
Oh.
Sorry. The omega squared is d theta squared plus sin squared theta d phi squared. Right? They just assume it. Spherical symmetric. What?
What about the R squared?
About the what?
The R squared.
Again, it's isotropic. Wherever I look, it looks the same.
Yes.
So I have. It makes sense to look at it from to use spherical coordinates.
Okay.
There could be a dependence on R. I get away from the source. Of course, R equal to 0 will be the source of the gravity. I get away from the source, I feel different gravity. If I go in to the right and to the left, go the same distance from the source, then I feel the same. Yeah? If I want to fully prove the Birkhoff theorem, what I would say is that I'm foliating the 4-dimensional space in 2-dimensional spheres, just filling it as 2-dimensional spheres. I'm not saying that because I don't think we need to get it. Because intuitively, the idea was supposed to be theoretic. Okay, so ds squared, generally, there is some GAA of A and B, dx squared, plus GAB of A and B. I have dA dB plus dB dA plus GBB of A and B times dB squared plus R, which is not defined, so it's some function of A and B. So R squared of A and B d omega squared. Okay, my 4 coordinates are A, B, theta, and phi.
Why
Right.
the order doesn't matter? DA, DB.
About what?
DA, DB, or DB, DA.
Wait, I don't yet know what. I'm just looking completely general. Completely general is a tropic metric.
Why don't you have like a dB, d omega, something like this?
No, I don't have. I have just R. I want something which is spherically symmetric. Right? So R is some radius, right, which depends on A and B. I did not say what. I didn't specify A and B. It's fine, right? So this is the most general metric that I have, which is isotropic. Now I can change coordinates, right? So coordinate change. Right, from A and B to A and R. Then I simply invert, right? Instead of R of A and B, I just write B as a function of R. Again, I didn't say what it is. Then I get ds squared is GAA now of A and R. dA squared plus GAR of A and R times dA dr plus dr dA plus GRR of A and R times dr squared plus R squared d omega squared. That I can do. Remember, A eventually would be representing somehow the time. Not there yet. No?
I didn't quite understand. You said that the time is A and the radius is
No. I just set up 2 coordinates. I said I have a 4-dimensional space. I have 4-dimensional space. Right? So 2 dimensions, theta and phi. That I keep because I want it to be isotropic. Then I have 2 other coordinates, and I don't know what they are. I just call them A and B. Really, they are T prime and R prime. They are not T and R. They're just. I'll get there to what they are. Right now, it's just A and B. And then I just wrote down the most general metric that fulfills this equation. this demand that is strong. That's the most general metric. And now I said, okay, now I start to do some manipulation. Rather than B, I want to switch to other coordinates, A and R. Yes?
Why cannot this R function be variable defined the function of B?
What?
Why can we transition to R, which R appears in the right hand side, right? Right there, right?
Yeah.
Why can we invert? Maybe it's not. Maybe it's not invertible.
Maybe it's not invertible. We're doing physics here. That's why I told you that I'm not going to go over through it. It's invertible in reality. You're right if you want to be very, very, not sure what is the right word to say, you can say, oh, maybe we can think of some function which is not invertible. But it's not. In reality, there is a solution. And remember the logic. We will derive a solution, we'll plug it into Einstein's equation, we'll see that it actually solves it. Right? The difficult part is to get the solution. Now, yeah.
dA, dr, and dr, dA, shouldn't they be computable?
Not necessarily. Again, you won't see it here because we have a lot of symmetries, but in more advanced or other solutions, such as Kerr solutions, you don't have to be. You have some clusters. Okay, the next step is to switch again to make another coordinate change. Now, rather than A and R, I want to work with T and R. So next, we want a new function, a new change, T and R, such that in the TR coordinates there are no cross terms. We don't want terms of the form dt, dr, or dr, dt. So we have dt is what? It's dt, dA plus dt, dr, dr. So we have the dt squared is the dt, dA squared, dA squared plus dt, dA dr, dA, dr plus dr, dA plus dt, dr squared, dr squared. What we really want is to remove instead of these three terms, we want something like m dt squared plus n dr squared. Or m and n are some functions. I didn't say what functions they are. But I can get that if I write down, right, m dt over the a squared is GAA. So if m dt over the a squared is GAA, and then n dt squared n plus m n plus m dt over dr squared is gr, right? Have your n dr squared plus m dt over dr squared, let's give it dr squared. And then finally m dt over dA dt over dr is gar. Yeah? So if I manage to find the solution, that means that I can replace these first three terms here with only two terms, m dt squared plus m dr squared. Yeah?
Can you explain again the second equation? Why with n?
Yes, I want to replace that part with that part, right? But n dr squared. So if I write down grr is just n plus here I have m multiplies by dt squared, so dt over dr squared. If this would be equal to grr, then I'm good. Right? If I manage to do that, then I can replace this term with what is written here. So I have three equations with three unknowns, which is t of a and r, m of a and r, and n of a and r. Right. So, up to initial condition of t, and assuming that I know what are the g's, I can get a full solution. So three equations, three unknowns, I have a solution.
The second order partial.
It's okay. What I want to do now is something much simpler than what you may think, right? What I want to do, I just want to say, okay, this is the most general metric for dimensional, which is isotropic. Now I want to see if I can write this metric in the most simple form that I can. What? Yeah, without the cross terms, essentially. And the answer is yes, I can. I just proved to you that I can do that. I did not specify what functions they are, and I cannot specify because I don't know what are the g's here. But what I did show you is that I can always write a metric, four-dimensional metric, with spherically, which is isotropic, in the form of ds squared ds squared is some function m of t and r. I did not say what it is because I don't yet know. Dt squared plus some function n of t and r dr squared plus r squared d omega squared. Now, so far, everything I did was completely general. I did not even, I didn't even try to solve Einstein's equation anyway. Right? I just say, okay, what is the most general metric that I have? And I showed you, what I just proved to you is that I can write any general metric in that. Of course, I didn't really say what is t and r. They are completely symmetric. I just multiplied r with the spherical or spatial case, because spatial coordinates, because I'm motivated by what I know. Now I put in. So far, there is no physics. Now I start to put physics. I'll just do one more step and then we'll go home. So the one piece of physics that I can put is that I know that very far from the origin, what do I get back? What do I get back? Minkowski, right? So that's called asymptotic flatness, right? So that means that when r asymptotically, namely when r goes to infinity, the metric should approach Minkowski. This property is called the asymptotic flatness.
This is the initial value. This is given just the initial values of the Tm and M.
Same thought it's a boundary value, there's no initial value here. But for me, what it really means is that what I want is that the metric must have one negative and three positive components. Right? So that means that the metric is pseudo-Riemannian. Minus one negative, three positive components. Which means that m has to be a negative function and n needs to be a positive function. I still don't know what is this function. Right? So rather than m and n, I can use alpha and beta to rewrite the metric. So I can write ds squared is minus e to the power 2 alpha of t and r dt squared plus e to the power 2 beta of t and r dr squared plus r squared d omega squared. Yeah.
You're using that in infinity m is negative, so you say it's always negative.
It's always negative. It has to be pseudo-Riemannian.
Why? Why pseudo-Riemannian is anything that's conserved along both space? That's why can it somewhere be zero and then become positive?
No, if the metric will get to zero there, it will not be invertible. Which means that it's not going to be nicely behaved. So the simplest answer I can give you is that this is outside the scope of this course. Okay? Yeah, if it has one sign, it has to stay with that sign everywhere in space. We did not solve Einstein's equation yet. We just wrote down general, this is just based on general arguments specifying what the metric should look like. I think historically isotropic. Okay, and approaching, well, I didn't even touch the asymptotic flatness. I just said it has to have one negative and three positive. So we still need to find alpha and beta. For that, we actually need to solve Einstein's equation. I don't think we have time to do it now, so we'll do it on Thursday. Yes, question. Question. All right, do you have any questions? Okay, so we'll continue to develop this metric on our next class. Now let's see if you send me back. Not particularly good. I see that 12 to 1 on Sundays. Nobody puts anything, and also Thursday at 9 a.m. Or for some of you who said maybe. What about 12 to 1 on Sunday, which is now basically? I'm not going to do anything now, don't worry. But I can ask, for example, Akshay to have a tutorial next week, Sunday at 12. So we'll have we'll finish, we'll have a break, and then there will be a tutorial. Is that okay with everybody around here? No? Any objection? All right. I'll talk to him, and of course I'll inform him. Right now we finish the class. We don't have that many more weeks to the end of the semester, but we're doing quite fine. We will cover what we want to cover. Anything else? Okay. Have a good rest of the week. See you. Good rest.